To this demonstration of the RaspiCar and the pilot net that I trained. So first introduction to the car, how it works again. So we have the Bluetooth controller. We can generally control the steering with the thumbstick, and we can control the throttle with the shoulder trigger, and we can also reverse throttle. In the past, the model was running, the neural network model was running on this accelerator stick. You can plug it in and you can accelerate neural network inference with it. Alternatively, you can also directly run pilot net sized models on the CPU if you quantize the models. So this is an additional optimization technique to make models run faster. And if you do this, you can also run it directly on the CPU. For the demonstration here, the model is running on my desktop PC. So since this is a node-based architecture, you can distribute nodes also across the network. And I can also start this node on my desktop PC now. And you can see that the camera images appears. And you can also see in the console, if you film a little bit closer, you can see the basically steering predictions. And here we have something which is called command input. And since we are not using the vanilla pilot net, but a command conditional model, we can change those commands with these shoulder triggers. And you can see that those commands change. And with the shoulder triggers, we can basically command the pilot net to go left or right, or if we press nothing, the car will continue straight. So we can now place the car on the track, and I can show you how the driving looks like. Sometimes, unfortunately, the car still has some electrical issues due to the electrical design on the car, so sometimes the vehicle may stop automatically, but then it will resume operation when it has enough current again to keep going. But for this test, what you can see, I will only throttle, and now where I have this node running, the node will automatically steer the vehicle. And it is a bit rough with my bicycle sitting there, so I can maybe put it a little bit like this. And we can continue to drive. So, for instance, if we want to take the right turn, I can command it, the left turn, I can command it to go left. And then I throttle again, and then you can see it will do the left turn. And if we now want to do the right turn, I can press the right command and throttle it again to go right. After I clear the junction, I release the command, because in those situations right now it is in a lane follow situation. Let's say we want to go left in this case again, so I press the left trigger again and throttle the car manually. You can see it handled it really well. So now I press the right trigger, do the right turn. You can also see I have some disturbances on the ground, which I included in the training to make it sometimes more robust, but it is not confused by that too much. We can continue to drive. And the route I'm currently driving, so I have it in my kitchen here and in my bedroom. It's quite a long route, and you can see the road layout that I have some T junctions, I also have X junctions here. And basically what I do with every model, so I continue straight now. What I do with every model is I drive those models across my flat. I have a dedicated path. Basically I drive with every model to assess the driving quality. And whenever an intervention is needed, I will count this intervention. And then in the end of the day, after I was driving for 5 minutes or so, I will have then a certain number for every model that I test, such that I can say, okay, this model has 2 interventions and another model has 10 interventions maybe. So we will go this direction now. You can see I press the trigger again. And let's say we want to take this turn again. I can again press the trigger. And you can see it works really, really well. Of course, the car is also able to recover itself from certain scenarios. So when I place it next to the track, and I just throttle it, then it will steer itself back to the track. You can simulate various displacements with respect to the track. You can also do some testing and cover up some roads with it. So we place it just right in front and see if it is confused by that. But you can also see it doesn't care basically, because also this was part of the training data where I did this augmentation in the training data acquisition. We can also, for instance, cover up parts of junctions like here. So now you can see the junction is partially covered, and I will now command it to do the left turn. So we will approach the junction again. I will press left, and then you can see that it also manages to take this turn, which is really, really nice, I think. So this is for the basically basic benchmark performance. So I assess the quality by driving around here, testing various things, and then counting the number of interventions. What we can also test is, for instance, I can place it here. And one interesting question also is, okay, when I, for instance, provide like wrong commands or inappropriate commands. So in this situation, it is a lane follow situation. Question is, okay, what happens if I now press, for instance, the right command, so that I command it to go this direction? It should behave in a way that it actually not continues right, even though I press the right command. It should just follow the path, in this situation, left, because there's no junction to do the right turn on. And I can test it. So I hold the right command, I throttle it manually, and then you can also see, for instance, it does the right turn, not the right turn, it does no right turn, so it behaves then accordingly. You can continue to do so. You can also vary the commands. You can also press a, for instance, left command in this case, so we force it to leave the track in this way, and we can also test this, and then hopefully you can see that in this situation also it behaves really well. Of course, if we approach a junction here, I have to release every command, because in this benchmark we want to continue to stay in this small circle here. So I release the command, go over the junction, and then, for instance, I can press again a misleading command and test it further. And I also constructed a benchmark besides the general driving benchmark. I have this benchmark where I continue in circles, and I systematically test 2 rounds counterclockwise, pressing left, then 2 rounds counterclockwise right. Then I do the same for clockwise direction, left and right. And with that I have 8 rounds in total. And I also count the number of interventions. And with that I have then a certain indicator or a performance metric to assess the performance of the model. So the model you saw currently all the time is a model that works really, really great, and it has included those inappropriate commands in the training process. So this is the reason why it is so robust against misleading commands. I can also show you a model that is more prone to errors to certain commands. So I load now a model that is where this inappropriate commands were not part of the training data. So this is this model, and I will just fire up the node again. And this is also the nice reason why I did it, the node running on my desktop PC, because I can easily and rapidly reload models, test models, and it's also a nice showcase that you can actually see that the distributed node setup also works, that you can run inference on different PCs. So it allows me to test a lot of models. I don't need to compile the models explicitly for the stick. I'm also not restricted to certain TensorFlow versions for the stick. And I can also load, in theory, arbitrary large models, because I have a very powerful GPU on my desktop, and the RaspiCar is a bit more limited with the Coral accelerator stick. So this is the reason why I have this desktop setup here. Okay, so back to the car again. So now I loaded the model that is more prone to misleading commands, and we will just do the same test as before, or like a small test. So I place it here. I press a misleading command, so I continue it to go right. And then in this turn, for instance, here you can see it deviated. And this is a clear deviation, because it is facing like perpendicular to the track. It has no possibility to recover. So in that situation, I count it as one failure, and I place it back on the track, and then I continue the testing. So I throttle again, I hold the right input, and then maybe you can see, it deviates again. So I put it again back to the track, and it cleared the junction. Now I hold the command, or I can, instead of the right command, I can also now hold the left command. You can see the car stopped because of the electricity issue. Okay, now we can continue. So I hold the left command. This is not a problem here, but in particular you will see when you go clockwise and counterclockwise, it always has a struggle. When you press the left command and it does a left turn, then it behaves somewhat okay. But if the path is followed or does a left turn, but you command a right command, then you can see it fail oftentimes, as we saw before here 2 times. Yes. But besides this robustness test for misleading or wrong navigation commands, generally this model behaves really well. So if I press commands as the model would expect them, so I press nothing because I follow the track. And now, for instance, I want to take this turn, I press my command again, and then you can see I take this turn. If I want to go this direction, I'll press the corresponding command to that, and then, oh, it paused. Now we continue, and then you can see it does the turn also really well. So the general performance for all models is really great, and it's just a matter with the wrong and misleading commands, and this is part what I investigate. And the cool thing is that you can see that certain models using certain training techniques are more prone to errors for this misleading commands, others are more robust. And those results I can produce here are also reflected in the simulation, or vice versa, which is pretty cool in my opinion. One general remark though is that since all models perform really, really good in general, so when you do the normal driving benchmark, I test a little bit here, then I drive to my next room. All models behave really well, which also is a difficulty in assessing the quality. Because when they behave well, you need to drive for a long time until one error shows up eventually. Oftentimes I have models that can do the normal benchmark perfectly well, so I have no intervention at all. But of course, sometimes you can see models, every model has a different flavor, kind of, and you can, as a human, observe, okay, well, this model is struggling maybe in turns a bit more, but generally all models manage to do all turns pretty well. And also, of course, I would also like to assess, for instance, the cross-track error, so how much the vehicle deviates from its ideal trajectory. This is unfortunately something that I cannot do in this setup because I have no localization technique here. The only thing I can really reliably assess is if the vehicle fails. So, for instance, if it deviates and goes like this is a clear failure. Or what I also count as a failure is when it deviates to a point where all 4 wheels are leaving the track. This would also be a failure, even though the vehicle might be possible to recover from this state back to this state. But as soon as I'm facing perpendicular or all 4 wheels are next to the road, it is counted as a failure. So this is basically the most reliable criterion I can have. Otherwise, of course, you see often models, some perform better and some are more centered on the lane, some are less centered on the lane. But it is always, as I said, really hard to assess the cross-track error because I cannot measure it all the time. I mean, I can see it and I can describe it as a human, but if we want to generate some reliable tables and have some reproducible results, then this failure criterion is a pretty solid one, even though it sometimes takes a little bit for the model to actually produce a failure. I think this is it. I can show you one more thing. So what I haven't told you is this model is a classification model, so it classifies between 11 different steering angles. One steering angle is the zero steering angle, the center class. Then I have 5 different classes for left and 5 different classes for right steering angles. You might think, okay, well, if I have steering angle classes, because originally this problem is a regression problem with continuous steering angles, if you do the classification approach, the steering might be a little bit choppy. But what you could see is it really behaves really well. And yes, the steering might be choppy sometimes, but usually, and I did it in the past, you can see no real performance gain or loss between a regression model and a classification model. But since the classification and discrete steering angles is a problem, what you can also do is you can smooth out your steering angles. So what I can do is I can enable this flag, and then we can load the model again. And what the pilot node now does is it takes all 11 predicted classes, and for every class we have a prediction confidence or prediction probability, and you now just do a weighted average of all 11 classes with respect to their probabilities. And if you use this technique, you can now also technically reach continuous steering angles. And this actually also works really well, and it smooths out the steering also. It's hard to see on the camera, But if I drive here, for instance, now you can see that the vehicle, by using this weighted average, also is now behaving really, really well, and the steering is a little bit smoother than before, but really there's no real performance gain or loss. So I command it to go this way here now. Yeah, so up the electricity was turned off. Yeah, we continue. Okay, so as you saw, for instance, this turn, according to my criterion, this wouldn't be a failure because there was still a wheel all the time in the track. But sometimes you can see they overshoot a little bit or they do a very steep turn. But generally, all models manage to stay somewhat in the track or on the track. And yeah, this brings me to the end of this presentation. I hope you enjoyed what you saw, and thank you.